Okay, so can you name that song and the movie that it made popular, made that song popular? Anyway, we're moving on today with a lesson on pH and pOH. And this one's again building on what we learned from our last video involving weak acids and strong acids and strong bases and relative base strengths and stuff. So I'm going to switch over to my notebook, and it should be it there. So I'll share that. Okay, so it's quite a mathematical lesson today. So hopefully you've had your breakfast and stuff like that, and you're feeling ready to go. Now, if you've done Math 12, if you've mastered that level of mathematics, I don't think this is going to be crazy challenging. But if you haven't, this could be a bit of a go. I know there's some grade 11s in the class, and some people have chosen not to do Math 12 for many different reasons. I don't know why. I mean, Math 12 is like the funnest course on the planet. But if you have done Math 12, you've done stuff on logs. So we are looking at some logs today, but not to the same level you would have done them in that chapter. That Math 12 really kind of goes crazy with the log section. Okay, so pH of a solution is related to the amount of H plus in solution, or as we now know, the amount of hydronium. We know there's no free-floating hydrogen ions floating in water. And the pOH, which might be new for many of you, is actually another measurement, another scale to measure things, and it measures the amount of hydroxide ions in solution. What's really important about these two descriptors is that they're not implying that something is acidic or basic. That's up to you to interpret. Many times we talk about pH, a lot of students will initially think we're talking about an acid, but a base has a pH, water has a pH, and acids have a pH. So, and the same goes for pOH. pOH is just a measurement of the amount of hydroxide that's there. So it's not saying something is basic just because you see the OH there. You could have an acid that has a pOH measurement, or water can have a pOH measurement, and obviously a base can have a pOH measurement. So I want to just sort of start off the lesson by saying that the pH and pOH, the words themselves tell you nothing about the solution in terms of it being neutral or acidic or basic. It's the numerical value of pH or pOH that would let you know that. So there's two formulas here, and this is where the logs pop in. The pH of a solution is right here. And that is the negative log of the hydronium concentration. And the pOH is the negative log of the hydroxide concentration. So I would encourage you to get your calculator ready. I'm going to grab mine. I've buried it under all my notes here. Hopefully I can dig it up. I got one calculator, and I got another calculator, but I don't. Well, there's my three calculators. I'm super eager to do some math today. Okay, so let's just let's just look on our calculator for the log button. Now, if you're using the school calculator, the one you would have bought through the office, you'll notice on the keypad the number 1 button, where 1 is, just above that you'll see LOG written there, and that's your log button on that calculator. So to access that function, you have to go second function number 1. Number 1, make it so. So second function 1, and that will access the log button for you. So let's just punch in a calculation, just to make sure we can all enter the numbers correctly. So don't worry about the negative sign here. Just type in the log of 10. If you're a Math 12 student, I'm sure you don't need a calculator for that, but just to see if your calculator is working, I'm going to type that in. So I go log of 10, and you get 1. And if you get log of 100, once again, just type that in your calculator, see if you're getting the same number as I'm getting. And so the log of 100, that would be 2. Now, once again, if you've done Math 12, you probably know you don't need to use a calculator for this, but if you have a harder question, like say the log of 20, well, 20 is between 10 and 100, obviously. So our number is going to be somewhere between 1 and 2. So I'm thinking 1 point something. And so if we type that in, log of 20 is equal to 1.3. 0, roughly, I think. Okay, so that's an important skill to have, and know the location of your log button on your calculator. But let's use the negative sign now, and let's just do the negative log of 1,000. And once again, we're just trying to get used to using the calculator here. So if you do log of 1,000 in your calculator, you'll get 3. But if you do negative log of 1,000, you'll get negative 3. And remember that this on your calculator is the negative sign, not the subtraction button. A lot of students, some students accidentally press the subtraction sign, and then sometimes it works, sometimes it doesn't. Their calculator sometimes does not understand what they're trying to say there. Okay, so here's a question. We're to ask, what is the pH of a 0.01 molar HCl solution? So if I take a look at hydrochloric acid, I have to know something about hydrochloric acid here. And if I go back to, I'm hoping I still have my data booklet here. There we go. Oh, perfect. Look at that. So that's from our last lesson, all these lines and stuff. So what I want you to do is just go to the very top of your data booklet, and let's just look at HCl again. So why I want to just review this is that HCl, hydrochloric acid, is what we refer to as strong acid. So that means it ionizes 100%, which means all of it completely gets converted into H plus and Cl minus. And of course, that H plus is actually hydronium. So when we go back to our notes here, and we take a look at this reaction, we would see that HCl, when we place it into water, it's going to go 100% into hydronium and chloride ions. So what's kind of nice about a question like this, when you're asked about pHs of things like HCl, since HCl is strong, you already know the concentration of the hydronium. Because if all of that compound was to be converted into hydronium, then the concentration of the hydronium should be the initial concentration of the acid. And you might remember in a previous video, I did mention that in a bottle of 0.010 molar HCl, technically there is no HCl in that bottle, which is kind of misleading. The label might be misleading, but it's actually the same thing if you said you had a 1 molar solution of sodium chloride. You know from the solubility chapter that sodium chloride is soluble, like really very soluble. So really there's no NaCl in that bottle. It would just be sodium ions and chloride ions floating around. So in the same context, an acid that ionizes 100%, there actually is none of that acid there. It's all in the form of ions. So since we know the concentration of the hydronium and we know the pH is a negative log of the hydronium, then we just punch it into the calculator. We say, well, that would be pH equals negative log of 0.010 molar. So what I would say is, why don't you guys try to get that? If you're a Math 12 student, why don't you try to get it without a calculator and see how you fare with that. So so I'll just use the calculators to confirm here. So I'm going to go negative log. You can't see me doing this. It's much more exciting if you're watching me push the buttons, but just imagine me pushing buttons right now. Negative log of 0.01, that's going to equal 2. And I'm going to write it as 2.00. And we'll talk about sig figs later. Okay, so let's say the question was, what is the pOH of 1.0 times 10 to the minus 5 calcium hydroxide? Now, calcium hydroxide, this is not technically how we would write a Branch de Lowry base, but calcium hydroxide, if we're told, now although calcium hydroxide has low solubility, we're being told that the solution is 1 times 10 to the minus 5 molar, which means that's the amount of salt that has dissociated in solution. So we should get calcium ions being produced and 2 hydroxide ions being made. And what we notice is that the ratio between the salt, the calcium hydroxide, which we know the concentration of, and the hydroxide is a 1:2 ratio, which means the hydroxide concentration will be twice that number. So the concentration of the hydroxide ions would be 2.0 times 10 to the minus 5 molar. So they are double the concentration. And so that would give us a pOH measurement equal to negative log of that number, 2.0 times 10 to the minus 5. Okay, now as a Math 12 student, even if you're someone really good at math, you really can't figure that out without a calculator. You might be able to approximate it though. I mean, the power on the 10 is negative 5. So you might conclude it's got to be close to 5. Maybe it's a little bit more, maybe a little bit less. What do you guys think? Well, let's just work that out. So this obviously I would encourage you to use a calculator for these kind of problems. So negative log of 2 times 10 to the minus 5. So I'm getting 4.6989. So let's say 70. Okay. Okay. So once again, we'll talk about sig figs and how all they play out in the end here. Okay. So there's two questions using the formulas that we talked about for pH and pOH. And once again, we're not saying the solutions are acidic, basic, or neutral, although you might be able to make some conclusions right now on what you think it is. But we'll talk more about that terminology a bit later and focus more on the mathematics in this video. So how would you determine the pOH of the question above involving hydrochloric acid? So that's the first one here. So this pH measurement of 2.0, what would the pOH have been if you tried to measure it? So we have to do a little bit of math here based on what we've learned before, and then we're going to teach you some other stuff, which will help you in a bit. But we have to remember about a concept called Kw, which is the self-ionization of water, which is the concentration of the hydronium ions. And if you don't know what this is, you really should go back and watch the previous video that talks about this. And this is 1.00 times 10 to the minus 14. So in order to find pOH, we need to know the hydroxide concentration, which means we have to know this number. That's what we have to find there. And what we know in the question above, at least with the HCl, is we know the hydronium concentration was 0.010. So we could just plug that into the formula and then work with that to figure out the hydroxide concentration, and then from that determine the pOH. So let me put that number in here. So this would be 0.010 molar, and you're multiplying that by the hydroxide concentration, and that still has to equal the Kw, assuming we're at 25 degrees Celsius here, which we kind of have to assume, otherwise we wouldn't be able to work with this question, or we'd have to be told what the new Kw value was. The hydroxide concentration would now equal 1.00 times 10 to the minus 14 all over 0.010. So when we work that out, we're just basically dividing it by 100th. So that's going to move the decimal 2 places for us. So we should get 1.0 times 10 to the minus 12 molar. Okay, and then if we wanted to use the formula now, we'd have to use this formula up here for finding pOH. And so we know the pOH of the solution would equal the negative log of 1.0 times 10 to the minus 12. And once again, as a Math 12 student, you probably can handle that. That's going to give you a pOH of 12. Okay, so that's something that you should be able to do. And once again, we're going to show you lots of tricks here. So please come back and rewatch this video. But what I would like to pay attention to is the number we got here for the pOH and the number we got up here for, the number we got for the pOH and the number we got for the pH. So this being 2 and the other one being 12. Something unique about those numbers that we're going to revisit again on that. But using Kw is a good way to figure out one of the ions you don't know, and then from that you could either figure out pH and or pOH. So let's say you know the pH of a solution. Can you determine the hydronium concentration? So basically kind of working backwards from this. Now this formula is going to be a little tricky if you haven't done Math 12, but for the Math 12 students, I kind of like to show you this because I mean, you've done Math 12. It's nice to know how mathematical formulas work. So I'm just going to take a look at the hydronium concentration and the logs and say there's our formula there. Now, as a log, normally logs have bases associated with them. So like log base 2 of a number, log base 3 of a number. But when we write log of a number, we actually are implying the base to be a certain number when we do that. So you might remember from math 12 that if you do that, the base is assumed to be 10. So that's base 10 logs if we do that. So what I'm going to do is I'm going to undo the log. In chemistry, they call it an antilog. But basically, we're just converting back to exponential. So the first thing I'm going to do is move that negative sign to the other side. So I'm going to go negative pH is equal to the log base 10 of the hydronium concentration. And then I'm going to convert from logs to exponents. So my base being 10 means that I would have 10 to the negative pH, and that would equal the hydronium concentration. So they refer to that in the book as the antilog. So it's the antilog of a number. So the hydronium concentration, basically you just go 10 to the negative pH. And I'm just going to write out the one for hydroxide here. It's derived the same way, so I'm not going to redo that for you. But that would be 10 to the negative pOH. So those two are two forms, or another two forms you'll have to commit to memory. So let's try these two questions over here. See if you can answer those two using those new formulas now. So what is the hydronium concentration in a solution with a pH equal to 3.50? And what is the concentration of hydroxide in a solution of strontium hydroxide with a pOH equal to 4.25? So why don't you pause the video and see if you can do those. Okay, so for the first one, we know that the hydronium concentration should be equal to 10 to the negative pH. So this would be 10 to the negative 3.50. So the hydronium concentration, if we were to use our calculator, so we're going to get 10 raised to the negative 3.5, and that gives us a concentration of 3.2 multiplied by 10 to the minus 4. And since it's concentration, it would be molar. I should have mentioned above that the pH numbers, the pH and pOH, they do not have a unit associated with them. So the pH of 7, we just say 7. But for concentration, obviously, we have to write it as molar. Okay, so next question. I told you the chemical here. I just want to see if I maybe threw people a little bit. But let's just do the hydroxide concentration here. So the hydroxide concentration is equal to 10 to the negative pOH. So this would be 4.25. So 4.25. And if we calculate that out, 10 raised to the negative 4.25, we get a molarity of 5.6 multiplied by 10 to the minus 5 molar. So that's basically how you use the formula. Now, sometimes we have to be careful of the compound we dealt with, especially when there's like a 2 here. Because if you look at the question above, when we did the pOH of this compound, notice that we had to times that by 2 to get the hydroxide concentration, because they told us the molarity of the compound, and from that we had to determine how much hydroxide we had, and that was of course in a 1:2 ratio. If you go down to this question, you'll notice that the strontium hydroxide would also be in a 1:2 ratio with the hydroxide. But what's important here is the pOH being told to us is 4.25. That's already telling us the sort of amount of hydroxide that's in there in the form of a pOH number, a log number. But it's not actually related to the compound itself. So the concentration of the hydroxide actually is 5.6 times 10 to the minus 5 molar. But if you were trying to find the concentration of the salt, or the concentration of the strontium, maybe, if assuming it was made by adding the salt to the water, then it would actually be half the concentration of the hydroxide. So in this case here, we don't double up on the hydroxides here because we're working with the pOH, which directly is related to the hydroxide concentration. Okay, so I just wanted to show the distinction. Sometimes we have to worry about that too, and sometimes we don't actually. If you know the pH of a chemical, can you find the pOH without having to convert between hydronium and hydroxide? So we showed how you could use Kw to convert between hydronium and hydroxide, assuming you knew one of them. So let's say you knew the pH, where you could definitely find the hydronium, and then you could find the hydroxide, and then you could find the pOH. But if you count the number of steps there, it's like 3 steps. So that's a lot of work to get to just, a quick question. So is there a quicker way to do that? And I wanted to come back to our thing we mentioned earlier, is that this number here is 2.0, and this number here is 12.0. Same chemical, measuring pH and pOH. So let's take a look at one more formula. And once again, this is going to be a little bit on the math side of things. Not that the other stuff hasn't been, but it's going to be a little bit creepier here. So let's take a look at, let's say, pH. So we said that was equal to the negative log of the hydronium. So I'm just going to do a little bit of review stuff here because there's a lot of different things going to pop out here. And we said that pOH is equal to the negative log of the hydroxide. And we said that Kw was the concentration of the hydronium multiplied by the concentration of the hydroxide, and that equaled 1.00 times 10 to the minus 14. Now, I wanted to go back and just talk about this number again, that this number really is only true at 25 degrees Celsius. We have to be at 25 degrees Celsius to get that number. So let's assume we are at 25 degrees Celsius. So let's take a look at another a term we haven't looked at yet. And let's look at what's called the pKw. So notice that pH is a negative log, pOH is a negative log, pKw is also the negative log. Now, it would be the negative log of Kw, though. Okay, so that'd be the negative log of Kw. Now, Kw, remember, Kw is equal to the concentration of the hydronium multiplied by the concentration of the hydroxide. And Kw is equal to 1.00 times 10 to the negative 14, sorry. Actually, I'm going to put it on this side. It's going to get squished in there. Negative log of 1.00 times 10 to the negative 14. I was going to scribble that out. Actually, I could use an eraser. That's even better. There we go. Looks much tidier. Okay, so we're going to do a little bit of math. We're going to change colors here. Now, if I take the negative log of 1.00 times 10 to the minus 14, if I use my calculator or just my math skills, I will get 14. Okay. Now, here's the tricky part. If I take the negative log of hydronium multiplied by the hydroxide, you have to know a little bit of log laws here. And that is the log of A times B equals the log of A plus the log of B. So I'm going to factor the negative out. And then this is going to be plus log of the hydroxide. Now, let's see how we did there. Okay, so let me pause here for a second. Sorry about that, guys. I just had a little knock on the door there. So this would be negative out. That. Now, if I put the negative sign back in, I would get the negative log of hydronium minus the log of hydroxide, because I have to put the negative into the brackets. So that negative sign there gets distributed in. Now, the negative log of hydronium is pH, and the negative log of hydroxide is pOH. So this would give me a new formula, which is actually a really useful formula. Different color, let's choose green. Green is nice. This would be pH plus pOH equals 14. Now you might remember up here, we said that this is pH 2, and this is pOH 12. And 2 and 12 give us 14. So anytime you take the pH and pOH and you add them together, you would always get 14, but I shouldn't say always, you would almost always get 14. Actually, you would always get 14 if the temperature was 25 degrees Celsius. Because notice we took the negative log of that number, and that number is only true at 25 degrees Celsius. So this would be true. Now, if you had a different temperature, I guess you could write a different statement, which would be the pH plus the pOH would be equal to, now it wouldn't be equal to 14, but it would be equal to pKW, where pKW is the negative log of KW, and then the KW would depend on what the temperature is. So at a higher temperature or lower temperature, you would have different KW values. But for most of the questions you're going to come across, that's what you're going to work with, is which is going to be the temperatures at 25 degrees Celsius. So off to the races, add the two numbers, you get 14. So the question was, it's kind of a, going back to the beginning, might have forgot what the actual question was, is if you know the pH of a chemical, can you find the pOH without having to convert to the other ions? So let's just say you were told the pH is equal to 4.0. And someone said, what's the pOH? Well, like one way to do this would be very time consuming and find out the hydronium. So you'd have to use the anti-log formula. And then from that, you could use the KW formula to find out the concentration of the hydroxide. And then you could negative log that, and you can get to that. But why not just use this new formula, and that the two numbers have to add to give you 14? So the pOH would be 14 minus the pH, which is 14 minus 4, which is 10.0. So, so this here is a nice formula if you know the pH and you just want to get the pOH, or vice versa. And please remember, though, it only is true if you're working at 25 degrees Celsius, that these would sum to 14. Okay, so here's just some other more colorful pictures I could find. The one on the left side here is just some of the formulas we've talked about. I think maybe they did a little typo here. That should be a capital H there. We can see these formulas are, and I'm not sure who did this actually, but that should actually be up there. I'm a little particular about where I put my plus and minus signs, but anyway, you get the general idea here. But I think a better chart is the one to the right. This is a really useful chart to try to get your head around. And basically it shows you how to figure out any of the four quantities that you're going to have to figure out here, and shows you the pathway to get there. So in the question above, the one we just did, we knew the pH, and we were trying to get the pOH. So you could go this way around the horn to there, and that's a lot of steps. You'd have to go up to H plus, which means you have to anti-log the number. Then you'd have to go over to hydroxide, which means you'd have to use the KW value, and then you'd have to go down to find the pOH. But obviously, a much faster way would just be to go that way, a single calculation. 14 minus the pH gives you the pOH. So this chart is really helpful to sort of get your head around and know how to jump between the various, quantities that you're going to want to figure out here. So let's take a look at this question. What is the pH of a 0.00? Maybe I'll just put both questions up. So why don't you pause the video and see if you can answer that. So the pH of a 0.0010 molar NaOH solution, and what is the concentration of hydroxide if the pH is equal to 3.33? That's a pretty cool number. Okay, so just pause the video and take a look there. Okay, so for the first question, they want me to find the pH, so I'm going to want to find this quantity. And I know the NaOH. Now, what I know about NaOH is it would dissociate into sodium ions and hydroxide ions. So you need to kind of know what my starting point is. Well, if the concentration of the salt is this number, and it all dissolves, it dissociates, then the concentration of the hydroxide is equal to 0.0010 molar. So I actually know this number, I know that number. And so I need to either go this way, or I need to go that way. And so I try to look for the least number of steps, but really there's no shortcut here. There's no straight way to go boom like that. So I'm going to need to do two calculations here for this question. I find that the pH plus pOH equaling 14 is a really quick calculation either way. So I'm going to try to find the pathway that includes that step. So the first thing I'm going to do is find the pOH from the hydroxide concentration, and then I'm going to find the pH. But you could go the other way if you want to, just whatever floats your boat. Okay, so let's find the pH here. So the pH should, or pOH, should equal the antilog of, what am I talking about? The pH should equal the negative log of the hydroxide concentration. So that's going to be 0.0010. And so that's going to give me, well, it should give me 3, I guess, but let's just sort of confirm that. But negative log 0.001, and that is 3. So 3.0. And now we're going to look at the pH of that. So the pH should equal 14 minus the pOH, right? Okay, it's just the formula. So we're going to plug that in. So basically we're doing 14 minus 3. So our pH should be 11.0. So, and of course 11 plus 3 equals 14. So easy peasy, lemon squeezy, pretty much. Okay, so we've got the concentration of hydroxide we're trying to find, and we know the pH now, okay? So go back to our chart here. I'm gonna erase all the stuff from the last question. And now I think I forgot. What is the hydroxide concentration? So what is the hydroxide concentration? But you know oh my goodness, what's happening with my computer? I'm not sure if you guys can see this, but I've lost part of my screen. There we go. We have the pH, and we're trying to get to hydroxide. So you could go this way. So you could anti-log it and then use kW, or you could go this way. And once again, I kind of prefer the 14 method. Just the math seems to be easier for me. But you know, once again, you guys are brainiacs, so whatever you prefer. So the pOH would equal 14 minus the pH. So I get 14 minus 3.33. So 14 minus 3.33. That's going to give, that is not true. There we go. Is equal to 10.67. So that's the pOH is what that is. And so then to find the hydroxide concentration, we just do the antilog of the pOH. So that would be 10 to the negative 10.67. And so 10 raised to the negative 10.67 gives me a pOH measurement of 2.14 multiplied by 10 to the minus 11 molar, which is really small. So there's not a lot of hydroxide concentration here, which actually, if you think about it, pH numbers, you might remember pH numbers below 7 are generally considered to be acidic. So a pH number of 3.33 is actually acidic. So having low concentration of hydroxide is indicator of an acidic solution. Okay, so what else am I going to talk about? Oh, I was going to talk about sig figs. Before I do that, I want you to just do one more calculation. It's actually a fairly easy calculation, but it might kind of alarm you a little bit. So let's say you had a bottle. I'm going to draw a nice bottle, a big bottle. Okay, big bottle. It's actually not that big. And it's because I can make it small. See, small bottle, but big bottle. Right, okay, there we go. So let's just make it normal size bottle. There we go. So I'm running, my brain's running too far ahead. Okay, let's go. Let's say this was 6 molar HCl. 6 molar HCl. And someone said, what is the pH of this? And what is the pOH? Why not? Let's do both questions. Because remember, pH and pOH, they're not telling you it's acidic or basic. They're just saying this is the amount of H's and this is the amount of OH's. So why don't you guys solve that question? Okay, so if I take the negative log of the hydronium concentration, I should be able to find the pH. I think I'll agree with that. And of course, if it's HCl, the HCl completely ionizes into H plus and Cl, which is really hydronium. So the concentration of the hydronium should be 6 molar. So we should just stick a 6 in there. So negative log of 6. And then something funny happens, and some students do not like this number. They get really bothered by this. Negative log of 6. And they get something like negative 0.8, say. Say what? Now, of course, if you try to find the pOH, the pOH is 14 minus the pH. So if I do that, I'm subtracting a negative number, which gives me a pOH of 14.8. Now, a lot of students don't like these numbers because they've sort of been told by their previous teachers in other subject areas of science that the pH scale kind of runs from 1 to 14 or 0 to 14, depending who you talk to. And there's no way you can get a negative number here. But the scale itself, although that is true that for most compounds for pH, they tend to like look at 0 to 14. And right in the middle of that is your 7, which is kind of neutral. And we're told that things on this side are generally acidic, and things, oopsie, on this side are acidic, and on this side things are basic. So a number like that seems strange for some people, but all that means is you would be below 0, like you would just be on this side. So do you think it'd be acidic or neutral or basic or nothing? It's like a oblivion or something. Well, you just be over here. You just be on that side of the scale. Just go over a little more, and there would your number be. So you can have pHs that are below 0. That's possible. You can have pHs that are above 0. You can same with the pOH scale, and that shouldn't be alarming for you. It's just that these compounds aren't typical compounds you would come across in your daily life. Like no one's walking down the street and just finds a bottle of 6 molar hydrochloric acid. These are things that you tend to find in labs or classrooms and stuff like that, if there was such thing anymore, that you could get access to, but it's very, very uncommon for you to get access to. So even in the stomach, when you're digesting your food, which I should probably go get right now because it's near lunchtime, the pH in the stomach is anywhere from 2 to 3-ish around there. Can change a little bit, I guess, but that would be somewhere like here on the scale. And those are numbers that we sort of more associated, but even in your stomach, like pH 2, that is really acidic. That is not, that's nothing to joke about. But a pH of a negative number is just in an area that probably most people wouldn't come in contact with. In fact, I think, I'm going to guess number, I might be wrong here, but hydrochloric acid, when it's purchased, when we buy it, it comes what we call conc. It's got the cool name like conc, which all it means is concentrated, and someone was just lazy and didn't want to write the other letters. But I think the bulk solution is around 24 molar. So it's kind of syrupy actually, but I wouldn't drink it unless I didn't, I don't know, like my teeth or something. Negative log. I got beautiful teeth. Come on, seriously. Negative log. Big book of British smiles, they say. So if I take the negative log of that, I get a pH of negative 1.38. So that's really far over. But once again, you're not coming across that in your daily life. That's just not something you would commonly see. Okay, so I'm going to stop the video there. We have gone through quite a few formulas, and once again, I would really encourage you to review this table, this chart. Sorry, this chart here. It's really useful to sort of figure out where you're starting and where you're going. And really, the most steps you should ever have to do is 2. Like basically, like starting in one corner and trying to get to the other corner. There's 2 steps maximum. I mean, I guess if you really wanted to, I did have a student on one test. They were trying to go from, I shouldn't joke about this, but sometimes as a teacher, there's just funny things that happen. And they were nice kids, so I don't mind saying, I just won't say their name, but they were trying to go from pH to hydroxide, and they actually went to there, and then they went back to here, and then from there they went to there. And it was honestly, I don't know if they were just joking around with me or what, but it was like 7 or 8 steps when I was watching them do this calculation. But you should never have to do that unless you're just bored. So anyway, I'm going to stop the video there. I hope you guys are doing well. I think you guys finished your test today, and I'll upload this video in just a little bit.